Hi there, and welcome to this installment of your roadmap to Web3. I'm super happy to be sharing today's tutorial with you. We love working with Web3 folks like yourself and the guys at Alchemy, right? At Chainlink, we love this. We love bringing all this learning to you so you can join us in this incredibly exciting and impactful space. So, my name is Zubin Pratap, and I'm a developer advocate at Chainlink Labs. Before that, I was a software engineer at Google, and before that, I was a corporate lawyer for 14 years. So the crypto space to me is super interesting, both as an engineer and as a lawyer. Now, I'm going to assume that having come this far, you already know what a blockchain is, what Ethereum is, what a smart contract is, and what NFTs are, because you're going to use all that know-how today. But first, I want to give you some context about what we do at Chainlink. Chainlink is a set of services that solves one of the most important and far-reaching problems in the blockchain world. This problem is called the Oracle problem. And Oracle is a trusted source of trusted data. And it's hard to do that on the blockchain. You see, the blockchain is a closed system. It is unable to connect with external systems. That's part of what makes the blockchain so secure and trust minimized. But it does mean that it's a hard problem to securely connect with off-chain resources. For example, connecting with data feeds and APIs. Another problem is that generating a random number, which has so many important use cases from gaming to security, is really hard. Why? Because blockchains have a consensus mechanism that is deterministic. And true randomness cannot be deterministic, otherwise it would be hackable. It wouldn't be that random. So that's where we come in. We build Chainlink to be the solution to the smart contract Oracle problem, to the connectivity problem, and to the cryptographically secure randomness problem. There's a bunch of other things we do as well, and we'll cover that in a bit. But first, let's consider a centralized Oracle. A centralized Oracle provides off-chain data, but they are centralized and becomes a single point of failure, which sort of defeats the purpose of a decentralized blockchain. But at Chainlink, we have built a decentralized network of Oracle nodes that are run by independent node operators. This provides security, trust minimization, and decentralization with off-chain data. The node operators aggregate the data off-chain, and then they deliver that data in a cryptographically guaranteed way into the blockchain. So, when your smart contract uses the Chainlink decentralized Oracle network, it becomes a hybrid smart contract because you combine on-chain and off-chain systems get the best of both. That's why tens of billions of value in DeFi is secured using Chainlink data feeds. That's why Chainlink's verifiable random function, the VRF, random number generator if you like, for the blockchain, is used to power dynamic NFTs with truly random traits. And we are going to build one of them today, right? Also, VRF is used extensively in a bunch of games and other use cases where we really need to cryptographically guarantee a fair outcome. Now, in addition to the data feeds and the randomness, Chainlink has also launched its own Keepers network. Keepers are a way to automate the execution of your smart contracts, so your contracts can keep working and be invoked without a developer input. Again, we'll use this today, so you'll see what I mean. Okay, let's get to coding. Just to summarize, today you're going to build a smart contract that uses Chainlink Keepers to automate its execution. You're going to connect to a decentralized Chainlink price feed through Oracle data magic. And then you're going to learn how to use VRF, randomness, to randomize your NFTs. I'll show you how to do all that. And we're going to start coding in Remix so that everyone can code along in their browser, don't have to worry about the environment. And I'll show you how to debug and develop these smart contracts in Remix and how to use and access the Chainlink Oracle networks. As a project, you get to deploy the final stuff into the Rinkeby test network and add some randomness as well. So let's go. Okay guys, so before we dive right in, let's just do a quick bit of setup. Okay, the first thing that I need you to do is to make sure that your MetaMask wallet, that you have it, keep your keys, private keys secure, of course, but make sure that you're connected to the Rinkeby test network. Okay. Now, we're not actually going to use this in the course of what you're going to watch in the tutorial, but you're going to need this in order to get your link tokens and everything else. Okay, so make sure you're always connected to the Rinkeby network. That's what we're going to be using as part of this tutorial. The second thing, of course, is to make sure that your Alchemy backend is set up, that you have the correct URL, because eventually you will need to connect you can connect your MetaMask, in fact, to Alchemy if you like, or if you're developing in another IDE and you want to run a bunch of tests and deploy it onto the network, use Alchemy to do that. The third thing I'd like you to do is go to faucets.chain.link. And then make sure that you connect your wallet. Now, when you first go there, if your wallet's not connected, it's going to show you a page like this, right? And then what you want to do is connect your MetaMask. Again, make sure that you connect with your connect to the Rinkeby network, because then the Chainlink site will actually read what network you're connected to and accordingly give you the right link token. So as you can see, it now says request test net link because it knows. And if you look at the URL, it knows we're on Rinkeby, okay? And so that's my wallet address. Get the 10 test link, get 0.1 ETH, and then I think it's rate limited. Once an hour you can do this. So in an hour, do it again, because you'll need this, you'll need link, and you'll need ETH if you're actually working on Rinkeby. Now, like I said, during the course of this video, we're going to do it all on Remix, and I'm going to show you box stuff for development. But for your assignment, you're going to have to put this on Rinkeby. And you already know how to use Alchemy, of course, so make sure that you have that all set up there. One last thing is the IPFS companion. So I've already got this installed, but it is a pretty handy browser extension, right? So get a hold of it, and what happens is it gives you this little icon here, like on the upper right here. If you click on it, it basically takes you to your node. What that means is you're running a node in your browser. So when I shut off my computer, you won't be able to access this node material, which is why you should get your own. And then in the files, you want to upload the images for the dynamic NFTs. Speaking of which, this is the repo. The links will be in the description, but here's the repo where you can get the code for this. And there are 3 branches. The first main, you can sort of that's just the starting point, and then price feeds is what we're going to cover extensively in the video. This includes your keepers, and then the third branch is the randomness, which is really going to be your little assignment for you to do, and you can check the code how I've done it there. Of course, there are different ways to do this, but check the code, get a sense of how to use it, and randomness is very straightforward to use and extremely powerful. So those are the setup tasks, most important of which, know where the repo is. You can look at the link in the descriptions. Set up your Alchemy, set up your faucets, get your link into your wallet, and make sure you connected your wallet to your Rinkeby network, and get the IPFS stuff going. And then what you can do is, once you get IPFS going, is you can pull the stuff out of the IPFS folder in the repo, and put all of these in your IPFS file. Now, you're going to need the JSON in the code, but the PNGs, the pictures, will also need to be sitting in your IPFS node. So just copy all of that. Once you've, if you clone the repo, or if you're just taking it out of the repo, that's fine. Just pull it out, send it to your IPFS. Make sure you have all of these files sitting in your IPFS so that your dynamic NFT can actually work. And that'll be particularly important because it's structured to work with OpenSea. Now, again, that's something that you'll do as part of your assignment, because it takes a little bit of time to reflect in OpenSea. Let's just jump into the code, Let's just jump into the code. Let's do that. Okay, guys, so let's consider what we're going to do now. First, we're going to create an ERC721 token. We're going to use OpenZeppelin, pull that stuff. I know you're really familiar with how to do that already. We're going to make it ownable. We're going to make it mintable and all that good stuff, right? That's the starting point. And then we start to layer on the different Chainlink services and pieces that we need to make this interact with off-chain components and compute, to make sure that that happens automatically, so that a person's not having to use their wallet to trigger operations on the NFT smart contract. We're going to connect into a price feed, probably use the BTC USD price feed, and track whether that's going up or down. And then we're also going to use VRF, so the verifiably random function, the ability to cryptographically provably generate a completely provably random number delivered into our smart contract, our NFT contract, and use that random number as the basis on which to decide which of the images we want to show for the NFT, right? That's the dynamic bit. So it changes based on the market condition. Market goes up, market goes down, our NFTs will change, okay? And it'll change, in a random way because of the VRF number that we're getting. So I'm going to show you all three of those pieces. Let's start with the ERC21 NFT token first, and then we'll layer on the other pieces, right? And there's quite a bit to cover here, so I'm going to try and go quickly. Remember, there's always the GitHub repo that you can look at. Take a look at the README, and I've set it all out clearly there about how we've structured this and layered it on, okay? Even the README is layered on. I've used different branches in the GitHub repo. Okay, so let's do this. So first, what I'm going to do is I'm going to create a new workspace, right? So this is on Remix. I'm sure you're already familiar with it now. So we're going to call this Chainlink Dynamic NFT. That's going to be our workspace name. I'm going to just delete all the starting stuff here. We don't really need this one. We don't need these three. We're not really. I'm going to just delete that for the moment as well, just so that it declutters the environment a bit. Fine, we'll leave all that stuff there for the moment. Let's just go straight to contracts, and we're going to create the first one. We're going to call it bull and bear.sol. Okay, so this is going to be our NFT smart contract, the ERC21 token. So we'll start with this, but let's pull it off the OpenZeppelin contracts wizard, right? So I'm just going to, I'd previously done this. So I'm just going to restart. There you go. So now we're going to call this, make sure you choose the ERC721. We're going to name it this. And I know that Vito and others have done this with you. So, all this should be straightforward. We're going to call it bull and bear. It's an ERC721. The BBGK is token. We're going to make it mintable. We're going to say auto increment IDs. And we are going to, can you see this on the screen? Yes, you can. Good. We're going to make it ownable. That's fine. We're actually going to add enumerable and URI storage. URI storage is going to be important because that's the bit that helps us update the token URI, which is going to be the image and the metadata for the NFT. Right, I think that's good. Now, for some reason, my copy to clipboard doesn't work at the moment, so I'm just going to copy and paste that bit, the whole thing. And let's put that into our remix here. Okay, so we've got bull and bear. That's where we want to put it. I want to just make sure the solidity pragma is okay. That's fine. Now, let's start. Let me just reduce this a little bit, and then we can start going through it. So you're already familiar with this because I know Vito has covered this with you in one of the early videos, right? So we're pretty familiar with this. But what we need to do is, why don't we quickly compile it locally? Now, I don't do auto compile. Only because sometimes I put chunks of stuff in there and it slows my remix down for some reason. So I'm going to compile this manually. And for now, I'm going to put it onto my local JavaScript VM, so my in-browser blockchain network, and that's fine. So I'm going to try and deploy. Make sure you choose the bull and bear, and then not one of the other contracts that we've imported. They all show up in the contract, so we just use the bull and bear one, and let's deploy it, right? Great. So now we can see that it's been deployed. Great. And down here, we can see the deployed version of the contract. We can see all these various things. So let's just quickly mint something to my address. So if I do a safe mint and put in my address, it should transact immediately because it's here. If I put my address in here, balance off should say 1. Excellent. If I say total supply, it should say 1. If I say token URI for token 0, it should just be an empty string. Exactly what we expect because we haven't set any of that in there. Great. Okay. Now, so what we need to try and do now is we need to make sure that we extend this smart contract, this NFT, to work with our keepers. Because the first thing we're going to do is set it up to be keepers compatible. What that means, and you can take a look at it here, is you can find this at the documentation, Chainlink documents about how to make your Chainlink keepers compatible. What that means is your contract is called an upkeep. Okay, that's the target. That's the contract that needs to be regularly called by the Chainlink service. So we call that the upkeep. Now the upkeep contract, in this case our NFT contract, needs to implement a certain interface in order for the Chainlink Keepers network to keep calling it correctly, right? And so what that actually means is that we need to implement two functions, which I'll talk about in a moment, but we end up having to make sure that our contract extends or is inheriting from the keeper compatible interface, right? And then by doing that, it means that we have to implement these two functions, check upkeep and perform upkeep. So take a look at the documentation, you'll get a sense of it, but you'll also see me doing this live now. So the first thing we need to try and do is we need to try and make sure, that this is Keepers compatible, right? So we're going to try and, you can just add Keeper compatible interface. Let's actually, and again, you can see all this in the branch called price feeds in the repo, but I'm going to just import a bunch of imports now for us, which are going to be relevant for the Chainlink stuff, right? So we're importing the aggregator v3 interface, which we're actually not going to use at the moment, but that's really for the price feeds. But for now, we're going to start with Keeper compatible, but let's just import the two, right? So Keeper compatible gives us the Keeper compatible interface, which is what we need to satisfy. And now let's go down. Okay, so what I'm going to do now is I'm going to add a bunch of things here around making sure that we have dynamic NFTs. The first thing that I'm going to do is I'm going to add the NFT tokens here, right? So, or the reference to the IPFS links. Remember how I've asked you to upload your files to the IPFS node, your companion, and so as long as your browser is up, you should be able to access that. So let me put that up here first and foremost. I'm going to put that in here. So these are just going to be a bunch of variables. So basically, I've divided them up into two, the bull URI from IPFS and the bear URIs from IPFS. There are three of each, and these are the JSON files on IPFS, right? So we put that in there. Now we also want to keep a compatible interface also requires us to basically use a couple of state variables, namely we need to make sure that we have the interval, right? We want to set an interval. So how it works is the keepers will call our contract and check whether the interval is passed. If it has not passed, it's not going to do anything, right? We'll see that in a moment. But if it has passed, it's going to run the upkeep, the operation. So let's just add that in here. So that's going to be a uint. We make it public for the moment because we want to be able to see it in our, when we deploy it on Remix, we want to be able to see it. And then it's immutable, which means we don't change it. But I think what we'll do is we'll make it changeable, right? And the reason for that, we'll just comment this out here so you can see it. The reason for that is we may want to, as we're testing, change the interval. We don't want to hard code it rather than redeploy the entire contract. Let's just update it, and we'll write a setter function for that. But normally you'd want to keep this interval, and I mean, up to you, but it really should be a steady interval that doesn't get changed or only gets changed by the owner, right? Okay, so we've added those two pieces of information. We also need to add a timestamp, right? So what's happening here? We're basically saying that this will also help us in debugging a lot. We're going to say that the last timestamp in which things were updated is going to be this, let's say. Okay, I'm going to take the opportunity to actually add a couple more things. One is since we already got this aggregator v3 interface, why don't I just add it here? I'm going to say aggregator, there we go, aggregator v3 interface. We're going to give this public, and we're going to give this an address, right? So we could always inspect it as well. Sorry, I beg your pardon. We're going to give this a variable, and it's public, so we can always inspect it. Now, what is the aggregator v3 interface? Well, that's the interface that we have to sort of implement in order to, or that's how we get a reference to the price feed, what's known as an aggregator smart contract, right? So the Chainlink network has a bunch of pieces to its architecture, and we as the client, as the user, as the consumer of a price feed need to interact with a price feed aggregator contract. So this interface is how we call the Chainlink, the relevant Chainlink aggregator, okay? And you'll see how we do that in a moment. We also want to just make sure we have, for sort of debugging and internal tracking reasons, we want to just see what the current price is. So we'll do an int 256 public so that we can see what it is, and we can call this current price, right? And now this is going to obviously default to being 0 because that's the default value for an unassigned int 256. Right, now that we've added these bits and we've added the token URIs, what we're going to do is we're going to sorry, excuse me, my throat gets really dry when I'm talking like this. We know we can save mint, we've done all that, right? So what we need to now do is in the constructor, right? We have the constructor. Yeah, let's pass in the information about the interval at which the upkeeps need to happen, and also the price feed contract, the aggregator contract we just talked about. Let's pass in the address. The advantage with that is we can make it configurable, okay? And it certainly helps in debugging as I talk you through this. So let's do that. You update interval. This is the interval at which we wanted to update it. And the next one is an address, and let's call this price feed, right? And then inside the constructor, we do interval, which is our state variable is equal to update interval. And we do that the last timestamp is equal to block.timestamp. So what we're actually doing here is saying as soon as we start this contract up, the block's timestamp gets allocated to the state variable last timestamp. That's going to be useful when we calculate whether the interval, which is the previous variable, has elapsed or not, right? Now this thing seems to be complaining here for some reason, so let me see what's the problem. Okay, it should be marked as abstract because we haven't actually implemented the keeper compatible interface stuff. That's why it's complaining here, right? It's saying that you should be marking this as abstract, but we're going to fix that in a moment. Okay, now that that's done, is there anything else that we need to do in the constructor? Yes, there is. So let me just comment this so you know what's going on here. I'm going to say this sets the keeper update interval data. And now we're going to do some more setup on construction. We're going to say, well, what is the price feed? Well, we have a state variable called price feed. Let's just say that's, and we're going to have an address passed in for the price feed. I'll show you how to mock this as well in a bit, right? So that it's faster than having to call a live contract if you want. But there are a number of ways to do it. But also the live contract, we can't update it. That's the whole point, right? It's a decentralized price feed. So in order to test and debug and show, I'll need to I'll show you, it's a very simple process to create a mock price feed where we can start giving it data and we pass that in the address in the constructor. And so we can change the price quickly to just make sure that our code works. So for the price feed, we're going to say this is an aggregator v3 interface, exactly that. And we're going to pass it the price feed address. And now we have an instant. We have a reference to that price feed contract, which is great, which is what we need. Yep, that's great. So what I want to also do here, and I haven't actually implemented this yet, but I'll be doing it in a while, is you see I've set the current price into here, right? So I want to actually instantiate that right away on contract construction. As soon as we deploy a smart contract, we should immediately get the latest price from the aggregator. Okay, so why don't we do that? We haven't actually implemented all this yet, but let's put it there so we don't forget to do it. Let's just call it get latest price, and this is going to fetch back from us from an aggregator the latest price for the BTC USD pair. Now I'm just going to copy and paste a comment from the repo here, which I'll put here so that it's clear. But this will also help me explain to you what we're doing. So what's happening here is we're going to set the price feed address. We're going to choose the BTC USD price feed on Rinkeby, and that's the address of the aggregator smart contract, right? So if you go to this address, you'll see the aggregator smart contract. In fact, let's just take a quick look so you know that I'm not lying to you. There we go. That's the aggregator smart contract, okay? And you can get this from the actual Chainlink documentation. So if I go Chainlink aggregator contract, we should be able to see down the feed registry, I think. Oh no, that's not it, sorry. Contract addresses for Ethereum data feeds. And then if you go down to Rinkeby and we see BTC USD, there we go. You see that address? ECE36 ends with a 404. There you go. ECE36 ends with a 404. And that's also what's here, right? So that's our Rinkeby based Chainlink aggregator price feed contract. That's the one we end up calling, okay? but we may want to pass in another one for mocking purposes and for local testing, but we'll get to that in a moment. Now, what's this saying? This is going to say that basically you don't have a price feed. Yeah, get latest price is not implemented. That's fine. We'll do that in a moment. That's what we want. Okay. Now, I just want to make sure. So we've got the safe mint. And what happens at safe mint? Well, let's update safe mint. Now that we have our token URIs in the IPFS array, let's update that to a default value. Okay, so we want to mint it to the address. That's fine, not a problem. We don't really need to pass in a string memory URI. Instead, we're going to use some that are already in the memory variables here. We're going to use one of these, but we'll use the 0th index just to get started. So we'll take that address out. So all that's fine. This basically increments kind of the not a problem. Set token URI. Here we go. So set token URI, we can just say we need to pass it a default URI. And let's figure out what we're going to make the default URI in a moment. As soon as I know how to type. Okay. And what we can do is we can say, well, let's make a string, and therefore it'll need to be in memory storage area. The default URI is going to be, let's start everybody off with a bull's NFT image, and let's just start with the 0th index. Okay, so that's the moment someone mints, they get the 0th index one, right? And what's the 0th index? So the bull 0th is gamer bull. So anytime someone mints a token for the first time, we should expect to see the gamer bull for any given token ID. Okay, cool. So we've done the set token ID, and I think we might as well just say default falls to gamer bull NFT image. Okay, so now that we've done that, what we can try and do is try to implement a few more things. We can forget a lot of the other stuff that we don't need at the moment. But the main things that we need to do here are to do, if you remember, making a keepers compatible contract requires two things. It requires check upkeep, and perform upkeep. So let's get to that because it's important that you understand all that. I'm going to just put some space in here for this stuff that the overrides required by Solidity that we got out of OpenZeppelin, because we don't really need that for most of this. So let's call check upkeep, which is part of the interface, the keepers compatible interface that we need to implement. And this is going to have something called bytes call data. And I'll show you what that means a bit later. And then something called check data. Sorry, the call data is called check data. But we're not actually going to use this at the moment. So let me just, in fact, we're not going to use this at all for the purpose of the tutorial. And I invite you to take a look at the documents to understand what these are actually doing. But that's basically data that you can send when you register this NFT contract as an upkeep, something that needs to be getting regular keepers interaction. You can arrange for that registration of this upkeep to send it a certain kind of data, right? Bytes basically that you can send it as input data. And the documentation, if you look at it here, talks about check data. You can pass information into your check upkeep from your upkeep registration, right? So that's what I'm talking about, that you can actually pass some data in here, and that's this data that gets passed in here. We don't really need that for what we're doing, so I'm just going to comment that bit out. And this is an external view function, and it overrides the parent that it's inheriting from, the keepers interface that it's inheriting from, and it returns a boolean, which is the upkeep needed, and then it returns also bytes, something called perform data, right? And so this is data that based on your computations, everything that happens in check upkeep is actually done sort of off chain, right? So you can do some pretty heavy lifting here, and it's securely done by the Chainlink network off chain, and then the result of that computation can be sent back. So it's really, the performance data of your off chain computation is what perform data is meant to be, but we're not going to be using it. So again, let's comment that. And you'll see why we don't really need it, because we're calling a price feed, and then we're just going to get that data, and that's just going to trigger a dynamic process to call random numbers and stuff like that. So you'll see that. Okay, And then upkeep needed is simply going to be a question of, well, have we actually gone past? So the interval, right? So we take the current block timestamp, right, which is a global variable available here, minus the last timestamp. So that's the time since we last updated the timestamp. And we say, is that greater than the interval? If, right, that's the condition we need to check. And that's what we're returning. So this upkeep, because we're assigning it the value of this this comparison, this is going to have a Boolean value, right? And that's what we return, a Boolean value. So that check upkeep is pretty much done, okay? And this is what gets called regularly. So when you register a check upkeep, let me show you, register an upkeep. When you open it, let's open that, right? When you want to register one of these, make sure your wallet's connected on the top. So mine's connected, right? It's connected with MetaMask. But if you want to register a new upkeep, you put in your email address, you put in the upkeep name, right? Which is a name, it's for you. It's not necessarily the smart contract name, it's the name for you to identify with. And once you've deployed your NFT smart contract, you put that address in here so that the keepers know which contract to call, check upkeep, and perform upkeep in. And this is, it ends up defaulting to your wallet address, which is the admin, that you have the rights to add upkeeps and change them and stuff like that. Gas limit, you want to put this at 500,000 if you're going to do it with our contracts, because there's a lot of computation that we're going to do, but you can get away with 200,000 as well. But if you're doing this after the video, if you choose to do this, use 500,000, I think. And check data is what remember we just talked about that information we pass in to our keepers, right? So that's the stuff we talked about here, passing information to check upkeeper. So you register all this and you make sure you fund it with some link, okay? Because this is a decentralized Oracle network, right? So these are compute operations that need to be paid for, and so that's why you need to fund. And we've already talked about funding with link tokens and how to get them from the faucet. You need to start with a starting balance. You can start with 5 or 7 depending on the price of things going on the day. You may find that it needs to go up or down, but start with 5 or 7 and you should be good. And then you hit register upkeep and your upkeep is ready. You can also manage your upkeep from keepers.chainlink. Because you can manage any upkeeps that you have. You can go to my upkeeps and see what's happening there. Okay. Now that we know that upkeep's needed, let's implement the perform upkeep, which is the second function required as part of the interface, right? That we're implementing, so that we make sure that we have access to the keepers network. So this one also gets the call data, and this one gets perform data, right? So perform data, if it was returned here, if we did some off-chain computation here and we return some data, that gets passed in here for us to use as part of the perform upkeep function. And we're going to comment this out because we're not really using this. This is also an external one, and we can actually call this manually from inside Remix, which is actually quite helpful because we don't need to wait for a keepers network to do it. We can start triggering the updates as part of the dev loop, and so that's great. So that's why I've marked it as external, and it has to be external because the keepers network is going to call it, right? Now, best practice is that you sort of run this validation all over again, right? So you don't do perform upkeep unless you revalidate. That's best practice. We refer to it in our documents as well. So if you look at the documents here, it says best practices. Here you go, revalidate, perform upkeep, right? And that's what we're going to do here. So I'm just going to take the same logic, and I'm going to say, just wrap it in an if statement, right? So if whole thing in brackets, then we want to do a bunch of things. Well, now that we passed the interval, we want to update the last timestamp for sure. We don't want to forget to do that. So we want to say that's equal to the block timestamp. Then what we want to do is we want to actually try and get hold, because this is the automation process, right? So anytime we pass the interval, we want to pull the latest feed data, price feed data. So let's get, we'll update that again. So the current price is the state variable. We don't want to use that yet. What we want to do is just say latest price, because we may need to do some computations of the old value and the new value. So we'll give it a new, we'll store it in a new variable here, an integer, and we're going to say get latest price, which is a function we haven't actually implemented yet, so it's going to complain again. And now we're going to do the logic, the dynamic bit. Okay, so if the latest price that we just got, right, is equal to the current price that we stored in the state of the contract, well, we don't really need to do anything. So let's just return. Let's not waste any compute on that, okay? Because the market hasn't changed at all. However, if the latest price is, let's say, less than the current price, then we need to do some things. We need to, well, this is going to be a bear market, isn't it? Or it's going to be a bear trend. So we're going to say, okay, update all tokens. Why don't we call it that? Update all token URIs. So let's do it this way. So we're going to pass in a string, and update all token URIs is, again, something we haven't implemented yet, but what we're going to do is, as you can see, it's getting called in the perform upkeep function, which means it's going to be dynamically changing the token URIs for all our issued tokens. Now, very quick point, you'll see it when we implement that, but it's going to be very expensive from a gas perspective. So if you're doing this on a pure Ethereum sort of testnet or LiveNet, it's going to be quite expensive and take time, right? You could try and do it on other things like Polygon. That's an architectural decision. I'm just going to show you the logic of how dynamic NFTs can be created using external upkeep calls, right? That call our smart contract, dynamically update them. However, keep in mind that this is an expensive way of doing it. There are probably better ways to do it, and other sort of opportunities you may want to consider from an architecture point of view. This is just purely to show you how the upkeeps work and how we can generate random numbers and how we can get price feeds. Okay, so if the latest price is less than the current price that we've got, and I misspelled current price, haven't I? Current price that we have in the actual state. Well, so this should be latest price. Good old complainers. So if the latest price is less than the current price, we update all the token URIs with a bear. And else, that means it's a bull run or bull trend at the moment, since when we just checked and perform upkeep. Well, then we do update all token URIs, and we'll pass it a bull. Okay, and we'll use these strings that we're passing in to do some logic and update all token URIs to figure out which of the IPFS files to show. Okay, now the next thing that we're going to do is, so we've checked the latest price that we've got back from our price feed, which we yet to implement. Right. Well, the only thing then that we need to do is update current price, because now that we've finished doing all the computation on it, we can say, well, the current price is equal to the latest price. And Bob's your uncle, right? So now keep in mind that all this is wrapped in an if statement, right? So if we are past the interval time, which means we're due for an upkeep action, then we do that. Now we don't have to do this. I'm just doing this so that you understand what's happening. Interval not elapsed, right? So basically what I'm saying is we're still within the interval period, so nothing's going to run. No upkeep. Now, this is actually never going to probably run, because we should only be calling perform upkeep if the previous check upkeep showed that it's past the interval. But since best practice says we're checking this, normally we wouldn't have this else statement. Okay, we just check, and when nothing happens, nothing happens. If you're not past the interval period, nothing happens. I'm just doing this here so you understand what's going on, right? You normally wouldn't see that in production code. Right, so we have that done. Now, we've used get latest price a few times, haven't we? So why don't we implement that? And now we get to actually implement our price feed, or the logic by which we pull out data from our price feed, which is kind of fun. Let me just show you where we can do this as well. So you can go to price feeds using data feeds, and you'll see this here. Right, so I think it's, no, that's the actual data feed addresses. So you'll see that for that, we basically use the aggregator interface that we've already imported, and we call the get latest price, well, we create the get latest price, and we call latest round data. So let's do that. Let's actually do that, right? So we know we want to implement the get latest price. Right, and so this is going to be a public function so that we can call it. It's going to be a view function because it doesn't actually change the state. It just calls another contract and returns what's already in that state. And it returns an integer that's 256 bits. And now this is interesting. So basically what ends up happening here is we call the price feed dot latest round data. That's it. That's pretty much all we need to do. Now, price feed, don't forget, is a state variable. Here it is, right? It's of the shape or of the type aggregator v3 interface. And in our constructor, we instantiated price feed, right, with the address that we pass in. So we could pass in that one, or we'll pass in a test or a mocking one shortly. Okay, so we have, all we're doing is we're calling latest round data, not date, on that. Okay, and so if we call latest round data, what are we going to get back? Let's take a quick look at the document so you can see it as well. If you call latest round data, you're getting a bunch of values, right? And you can actually go to the API reference here as well and take a look. If you call get round data, which is, oh no, we're calling latest round data. Here you go, right? Get the price from the latest round. Now the aggregators work by doing rounds of aggregation, so that's what they mean by round, right? The latest round of aggregation has produced a bunch of data. This is all the data that it produces, right? The round ID, the answer, which is the actual price, up to the number of decimal places, what time it started, what time it got updated, and answered in the round. So this is all the data. It explains all the return values as well. Now, one thing to note is that answers are always, because Solidity doesn't support floating point, it's just one long big number, right? But the actual price feed, see how we went to this Rinkeby testnet thing in the Ethereum addresses, right? So it's Ethereum data feeds, and you look for the Rinkeby testnet, and we're going to be using BTC USD, right? If I click on show more details, right, and now I look for BTC USD, you'll see that it has DEC, right? That 8 means that it's 8 decimal places. So the number that comes back from that, the answer, the int 256, for our particular data feed, because we're using BTC/USD, for that one, we're going to have 8 decimal places. So let's implement that. And what I'm going to do is I'm going to actually go back to this document, and I'm just going to copy this because we're not going to use any of the data that's returned except for the price. Okay. So we're going to say that's equal to the price feed. That's pretty much what we saw previously as well. Now, an example price, and I'm just going to copy this from the repo, right? An example price will look like this. And that's, in our case, it's going to have 8 decimal points, right? So something somewhere around here, I'm guessing. Yeah. So it's actually going to be that. But what gets returned is that. Okay. And so you can compute, you can see in the documents that it says, if you look at the API reference, it says that there's a function called decimals, which gets the number of decimals present in the response value, right? But you can also see it here in the extra data field in the actual feed contract numbers directory, right? So we know it's going to have 18, but we're not going to worry about that because all we're looking at is up or down. We don't need decimals for that. We just need to literally compare two integers, right? And so this returns an integer. So that means we need to actually return this. So we can say return price. Okay. Here. And that's that. So get latest price is now implemented, and it does return the price, which is good. Right. So now that we've done the get latest price function, let's move on because we need to, you'll see that the compiler is complaining here, right? Because we need to implement update all token URIs. And I think what we'll do is do a couple of helper get functions as well for some of the state variables that we've declared. So let's do the update all token URIs function, right? So do update all URIs token, and we'll think in a moment about what sort of arguments we want. Well, we were already actually passing it in one of these strings. So it'll be a string memory, let's call it trend, right? Because that's what it is. It's a market trend. This is only going to be called internally because we only really ever call it as part of this perform upkeep function. It's not meant to be called externally. You could if you wanted to, but in general we don't really need it. When I'm showing you how to debug and how to run mocks locally, you'll see that we don't really need to make this an external function. Now, what we're going to have to do is we're going to get a string in here, and we're going to have to check whether that string is equal to bear or bull. These are the two options, right? You could do an inner, and maybe in fact, we could do that for the assignment, which I'll give you in a bit about doing randomness. But we need to compare strings. Now in Solidity, one of the ways we compare strings is we often use a helper function. You can look this up on Stack Overflow or something, but I'm just going to put some helpers here, and we'll implement a couple. But the first one we want to try and implement is compare strings, right? So we want to try and compare two strings. So we're given string memory, let's call it A, and string memory B. These are the two strings we want to compare. And what we want to do is we want to return a Boolean, but this is going to be an internal function. It doesn't affect state. It's not even viewing anything. It's just pure. So we're going to call it internal pure, and it returns, I keep doing that, don't I? It returns a Boolean. What Boolean is going to return? Well, we need to basically compare A and B. So how we do that is we do the following. We do a Keccak 256 compare. We hash it using the Keccak 256, but the actual comparison is done with the global sort of functions that come with Solidity called encode packed, right, which is part of the ABI object. And what we do is we basically encode packed A, and we check its equality with, oh no, actually we do it with the hash. We hash two things. We do Keccak 256 of A, and then we do Keccak 256 of the B string. And that way we get, yeah. So we basically check that, and we want to return this because this is the Boolean, right? So we check whether or not these two have equality by Keccak 256ing them, which is basically a hash algorithm. We hash the strings, and we check whether the hash value is identical, which, hash should guarantee that identical input, identical output. So it should guarantee that, and therefore we just check that they're equal, in which case it is a true. We return a true, which is what's happening here. So back and update all token URIs. What we want to do is we want to compare the strings and accordingly have conditional logic. So if compare strings, we want to check first whether it's either a bull or a bear. Let's start with bear, right? So if compare strings bear is the same as the trend, then we do something. Otherwise, it's going to be bulls, right? So then we do something else. So we want to update all the tokens. So what we do here is we know, now this is the bit that gets really expensive, right? On an Ethereum network, for example. So you may want to consider from an engineering point of view how you'd optimize it, or whether you're using other sort of layer 2 solutions and so on. But what we're really going to try and do, we need to update all the NFTs in supply. And we know that we have the counter, right? So the counter tells us when we call current, it is meant to return to us the value or the token number of the one we're going to mint. So that's why we call it current, right? So the current will return us the total number of NFTs out there. So what we want to try and do is we want to check, we want to loop over all our NFTs and do something. And what are we going to do? We're going to loop over them. So we're going to say we'll start with 0 because our NFT minting starts with token ID 0. So let's do that. And then we're going to say if I is less than token counter, you remember we have the token counter, which is imported thanks to, token ID counter, I think that's it. It's imported thanks to our imports from OpenZeppelin, the counter module. So get the current value. We iterate all the way up to that, right? So we start with 0, iterate all the way up to, but less than that because of 0 indexing. And then we say, well, we're going to set token, for all of these, we're going to set token URI to something different, right, for that. So set to token URI takes 2 arguments. One is the token ID, starting from 0 onwards. And the second is, well, what's the actual URI string that you're going to pass it to? And because this is bear, we're going to pass it the bear URI's IPFS array. And we're going to give it 0 for now, right? Because the assignment will be for you to introduce randomness, and I'll show you very quickly what you need to try and do for that. And you always have access to the GitHub repo as well, where the solution is provided. So what are we saying here? We're saying that if it's a bear that gets passed into update all tokens, well, set it to a bear NFT image, right? And we'll start with the 0 one. And we do this for all tokens that we've minted. Otherwise, we'll need to do the same for loop again, because we only execute this for loop depending on which if condition is satisfied. We just change this to bool URIs IPFS, right? So all we're doing is, depending what trend it is, we iterate over all the available tokens in circulation that we've minted, and we update it with the appropriate trend related NFT image. So this is what makes it dynamic, right? Now, we have a couple more helpers that I think we want to try and do. Actually, what we should do is we should also just do we should probably just emit an event here so that we can look at it. You know, if you look at OpenSea, for example, or if you look at the Etherscan for this contract, you'll end up, if once we're on Rinkeby, you'll see that you can look up emitted events. So this can sometimes be useful. So let's try and emit a token updated with a, well, let's just give it the trend, right? So we can see whether the trend is showing through or not. So we need to now declare the token, the event. And for that, we could go up to the top, perhaps here, and we can go event token updated. Actually, it should be tokens. I'll change that down there. Tokens updated, and we'll make it string with a market trend. Yep. And so that's what we're going to try and get into. Cool. All right. So now going back to our update all tokens, we see that it calls, where is it? It's down here. There we go. If it's a bear, it'll update all the tokens with the first of the bear array. And if it is a bull market or bull trend, it'll update it with a bull. Fine. And we have to update this to tokens updated, because that's what we're calling the event. And the important semicolon. Okay, so now we're emitting events also. Now let's do a couple of the helpers of the set function. So we got an interval in the state variable, which is the interval after which the keeper will run the perform upkeep function, remember? So let's do a setter for that. Now we normally wouldn't have this, but we'll do it so that it's easier for us to debug it. So we'll do set interval, and we take in, I think interval is a uint 256. And so we take in the new interval, let's call it the new interval. And this is going to be state changing, so it's not going to be a view, but it will be a public function. And you know what, let's mark this only owner, right? Only the person who deploys the contract, because you'll remember that our contract is ownable, right? Which is inherited from OpenZeppelin contract library. So we want to make sure that only the owner can call this set interval function, right? So only the person who deployed it. So not anyone can publicly call it like that. Just the person, which is us, because we're going to deploy the contract for now. But you can change ownership. That's a different topic though. And so we want to make sure that the interval has been updated to the new interval, and that's that. Now we also want a function to set the you remember we have the price feed address that we pass in, right, in the constructor. So in the constructor, you'll see here, we're passing in this price feed address, which that gets instantiated into the price feed state variable. Now we'll do it with the mock to begin, but you may want to update it rather than redeploying the whole contract. You may want to update it to the final Rinkeby contract address for the price feed, in which case you shouldn't have to redeploy the whole contract, just update it using the setter. So that's why I'm doing it here. And so this one will be, we can call the set price feed, and it takes in an address, and we'll call it the new feed. Again, this should also be the same signature as above, so public and only owner. And this will update price feed to be, do we call it with a capital F? Yeah, we did. Price feed. is equal to aggregator new price feed. Oh, what's it called? New feed. Yeah. And so with that, we now have a contract that's still complaining. So let's take a look at it. It's because we didn't finish our event with a semicolon. Okay, so now remember that we OpenZeppelin, the standard ERC 721 spec with the enumerable gives us the token URI. So when we call this, and it's a public view function, so when we call this, we should get the applicable token URI for that given token ID. And the token URI gets dynamically set in update all token URIs, right? So that's why we update the set token URI. So when we call token URI, we should get the updated one. And the only time it gets changed is when perform upkeep runs and there's been a change in the price feed data, right? If the price feed hasn't returned data that's changed from what we already have, so the latest price is equal to what we already have, the current price, there's not going to be a change in the dynamic NFTs. So just keep that in mind. Right, so I think that's pretty much covered most of what we got here. Let's try and compile this. You can use the 8.7 compiler because I think I have Pragma 8.4 here. So let's compile Bull and Bear. And let's just locally deploy this on our JavaScript VM. You should have by now, in any case, connected to your Rinkeby network if you need to. So you can just do injected Web3 if you need to, but we won't here, right? We're going to go back to JavaScript VM London, right? Which gives us our test accounts here. And I'm just going to deploy this. Oh, I can't deploy it because I have to pass in. See, it says you haven't given me the right arguments. So let's put the update interval. It won't matter for now, but let's put it as 10 seconds. The number denotes seconds. And the other thing we needed to do is pass in an address for a price feed. So what we can do for the time being, let's pass in the actual. Oh, we can't pass in the Rinkeby. That's right. We can't pass in Rinkeby because we're running this locally, which means we have no choice but to actually produce our mock because we're running this locally in our browser. So great, excellent. Let's do the mock. Now you're going to love this because this is pretty straightforward. Let me just open up this. So on the Chainlink GitHub repo, right, you can see that if you go to Chainlink, go to contracts, source, version 0.6, tests, we have a mock v3 aggregator solve, right? So there's already a contract out there that's available for import. And what we want to try and do is we want to basically import this, and that's pretty much it. That's how we get a mock. So let me show you how we do this. We just create, we just create in our contracts, close all this out. We can just do here a new file, and we're going to call this, let's call this the mock price feed dot solve. Okay, and this one's going to be pretty straightforward. What we're going to do is we're going to just say pragma, the usual SPDX license identifier call MIT, and then what we can do pragma solidity. Isn't that what we had? 0.8.0, I think. Oh, 0.8.4. That's fine. We do that, and then all we have to do is we import this business. That, right? So we can do import at chainlink /contract /source /p point 0.6, I think it was, yeah, 0.6 tests mock aggregator, mock v3 aggregator, right? So we import that, and believe it or not, that's pretty much it. It's pretty cool, except that it's complaining here about something. Really? Oh, that's why. Oh, now I've got an error complaining that the source file requires a different compiler version. All right, so the source file requires 6. So let's just compile it with 6. Let's just compile with any of these 6 and see if that works. Oh, fine. 6.4. There we go. All right, now we've compiled that. So just keep in mind that the Pragma solidities are going to use different compiler versions, right? So we'll compile that, and then we'll go down to mock v3 aggregator. So now that we've got this little import statement, basically all we need to do is that we need to compile it. So we compile it here, make sure that your pragmas are correct and that you've chosen the right compiler here that matches your pragma statement. Run the compile, and then we make sure we choose the mock v3 aggregator because that's all we've imported into this one. It's going to show up as that. And then it takes 2 arguments. So if you look at it, it takes in 2 arguments. It takes in an initial answer because it's a mock, so you have to give it a seed, a starting point answer, and the number of decimals. So let's just pretend we're doing the same Bitcoin USD one, right? So we'll give it 8 decimals. And for the starting value, if you look at the repo as well, I've got it there. But I think I said in price feeds, it looks, there you go, an example return price is that. So let's just give it that. So now I need to go back to the right contract, go to mock3v aggregator and give it 8 decimals, and then paste in that number that I pulled out from my bull and bear sol file, right? And JavaScript London, we're good to go. Let's just deploy this. Great. Now let's just take a look at how we interact with this. The important ones that we need are, remember how we were doing latest round data, right? So that's what the bull and bear contract asks. If you remember, get latest price is price feed dot latest round data, and it returns all these things, right? Of which we're only using price. So let's try and run that latest round data. There you go. You get the round ID, we get the answer, which is actually the exact number that we fed it in when we copied and pasted it in. Oh, we don't have that here. But it's the same number as this one. 303 ending with 1688. That's the one we got here, right? So that's a mock price feed right there, right? Because we're not on the Rinkeby network yet. We're just doing this locally. So I'd suggest you do this, follow along. We'll do this in this video. But you can put it on Rinkeby when you're ready, and you can use all the information I've given you here and in the repo. But the principle is the same, right? You'll have, this will be the contract you use out there in the real world. Only you need to pass that in to your constructor function in your bull bear, your Solidity contract, your NFT smart contract. You pass in the price feed address, right? Pass it in the one that's on Rinkeby. But now, since we're doing it locally, what we're going to do is we're going to copy this local mock one's address, and I'm going to go back to bull and bear here, just recompile it again just for safety, and then we go to bull and bear, and then now we should set our update interval to 10 seconds. Why not? But we'll do it manually anyway, so it doesn't really matter. But in real life, keep in mind, the more often your keepers run, the more link you're going to use up. So you want to find the right balance for how often you want them to run. How important is it for your application that it runs often? You can even set it to run every day, right? 24 hours worth of seconds, right? Or you can do it every hour, whatever you like. For now, I'm just going to put it at 10 seconds because you'll see for development, our logic around perform upkeep won't work, or check upkeep will come back as negative if the interval is not elapsed. So we want a short interval for development so that we're not running into that if statement block. And the second argument that we need to give to bull and bear here is the price feed. We'll give it the mock, not the one on Rinkeby, because we're local. We're not going to be on Rinkeby yet. And so we give it the local one. The local one's copied from down here, mock v3 aggregator. And we deploy that, right? Great. So that's been deployed. So now at the bull and bear one, we should see a bunch of things. What we can try and do is we can try and see, you remember that on constructor, when we created the bull and bear, we set the price feed, right? And then we also called get latest price. So we should expect that when we hit current price, we get this number that we passed in a little while ago, this 3034 ending with 1688. So let's just check that, right? There you go, we have it. So that means immediately upon the creation of the NFT contract, this bull and bear smart contract, it called get current price, got it from a mock and populated that. Great. Now let's just check the total supply. 0. Makes sense. We haven't minted any yet, right? If you look at the price feed state variable, we'll see this is the same address as our mock. So this is why I added all these things to the state field, is so that we have access to all these state variables and we can see what's going on, right? So 0xd91, and that's what 0xd91, right? So we know our price feed set correctly as well. Great. Do we have any tokens? No, we don't. So we should expect token is URI for token ID 0 to revert, right? There you go. It reverted because it said non-existent token. Great. So this is working fine. Now let's grab our address up here because we'll need it in a moment, our account address, our wallet address, and let's do a couple of things. Let's mint to ourselves, right? Let's do a safe mint. And so we should have that transaction because it's so fast because it's locally on our browser. Let's check total supply. We should now see this as 1. There it is. And because we minted token number 0, we should have token 0 should return our gamer bull, our default one. Remember, we set it here. We set the default bull immediately on minting, on safe mint. Here you go. The default bull is the 0th index, which is gamer bull, right? So that's working exactly as we thought. If we try and get the token URI for token URI for token ID number 1, which hasn't been minted yet, we'll have the same non-existent token error. Great. So that's fantastic. And if I put my address in owner of, right? So that's another ERC specification. I give it my wallet address, click owner of. That was the wrong one. Sorry. Owner of token 1. Sorry, token number 0. That'll give me my wallet address 5B38, which is what my address is here. Cool. Okay, so our Bull and Bear NFT token seems to be working. Now we need to try and do 2 things. We know we've already done one price check. We already got the latest price from the actual mock contract, right? But let's just make sure that if the aggregator were to change its price, whether if get current price would still work. It should, but let's just do it anyway, right? So we go back to our mock aggregator and we update the answer. And what we can do is we'll start with that number, but let's try and make the number go down. Okay, so 303. So now we're going to say, okay, well, the price is, so the current price, the latest answer is 3031688, which is what we're putting in now. But now we're going to drop this. Let's drop it to 28 something. Okay. And we update it. That's going to be a transaction because we're changing the state of the blockchain. If you're doing this on Rinkeby, you'd have to sign in MetaMask and all that, but it happens instantly here. We've updated the answer. Now, if we click latest answer, it should change from 303 to 283 something. There you go. It's done. And if you do latest round data, you'll see that also changed to 283. So now we know our price feed is telling us that the price has dropped a bit. Okay. Let's just go back for a moment to the token URI for the first token that I issued myself, token 0. And we'll see that it's got the gamer bull. Okay, so the default is a bull because the trend we start with is a bull trend. Okay. Now let's make sure that we understand the correct price, current price according to our token smart contract. The ERC 721 smart contract is 303. It hasn't updated yet. Okay. If I run perform upkeep, right? That means we assume that the keeper is already, so for example, before I do that, actually, let me do this. If I do check upkeep, which is to see whether my upkeep is due, it checks the block timestamp, it checks the last interval and all that. In fact, you can get the interval here by hitting interval. You'll see the interval is 10 seconds, right? You'll see the last timestamp was 16527742002. So now if I do check upkeep and you pass it bytes, which is basically pass it an empty array because we're not using those arguments. So we check the upkeep to see it should return true or false. Is an upkeep due or not? If it's due, it'll return true. It's well over 10 seconds, so it should be due, true, right? So yes, upkeep needed is true. Great. Now let's simulate what the upkeep would do, because the keeper, once you register the keeper and it knows what the interval is at every block, every time a block is added to the blockchain, it'll check your check upkeep and see if it's returning true. If it's returning true, your keeper, registered keeper, is going to call your perform upkeep function, right? And so you do, let's simulate that by calling it directly ourselves, perform upkeep. What we were expecting to see is a bunch of transactions should propagate. It should check the price. So when perform upkeep happens, let's refresh our memory, right? It checks, yep, it's going to be due. So it does that. It gets the latest price. We'll see that the latest price according to our smart contract is 303, but according to the aggregator, according to the price feed, it's actually dropped to 283 something, right? Our contract doesn't know that yet. It'll get the latest price. It'll compare the price. It should see that, oh, the price has actually dropped a bit, which means I need to update all token URIs with a bear. It should then execute update all token URIs with the bear trend, and it should set the token to the bear one. We're at Gamer Bull at the moment. It should set it to bear, okay, to one of the bear ones. In fact, let's take a look at which one it should. So which is the first bear one? The first bear one is Beanie Bear, okay? So we expect update all token URIs to then actually set this to the Beanie Bear, which means after we call perform upkeep and perform upkeep runs, it gets the latest price from the price feed, updates the state of our smart contract. It then updates all the tokens that are issued. Right now we have only one, but there could be 100, right? Which is why I said it could be very expensive to do it that way. But it does the upkeep, it checks all of them, it changes it. It's running the bear market logic. And so it should, when we click on token URI for 0, after we run perform upkeep, this should change from gameable.json to beaniebear.json, right? If that is the case, then our contract works. Then the entire thing works and we're done, right? So let's see how we go with that. So perform upkeep, pass in an empty array, which is what bytes is, and let's see what happens. Okay, so it happens almost instantly here. Now, our total supply should not have changed. That's still 1. The owner of 0 will still be me. And then if I do token URI, this should change from gamerbull.json to beaniebear.json. Let's see if that happens. Yes, excellent, it's done. So let's quickly recap what happened, right? We have our keepers. We register our keepers, and the keepers calls our contract every time a block is mined on the blockchain. Our contract will tell it, are we due for an upkeep or not, based on the interval. If we are, the Chainlink Keepers network will then call the perform upkeep function. The perform upkeep function will have the logic that actually does the stuff that needs to be done on chain. The check upkeep can do stuff that can be done off chain, that's fine. But in our case, we're doing a bunch of on chain things. What are we doing? We're updating all the token URIs based on the latest price from the price feed. So when we do perform upkeep, we call the get latest price function, right? If there's a price change, we work out whether it's a bear trend or a bull trend. And accordingly, we update all tokens with that logic and say, hey, if it's a bear trend, set it to bear one. If it's a bull trend, set it to bull one. Okay. Now, that's pretty much the logic we've done here. We can quickly run through this again if you want and change the price to a bull, right? So make the price go up. Right now it's 28. Let's take it up to 38. Update that. That's in the mock aggregator. Go back to our NFT smart contract. We'll see that the current price is now 28, which is what we thought because the last time we dropped it to 28. Now, we should, if we run perform upkeep, we should expect current price, we'll check, to change to 38. And two things, we should expect token URI for the token number 0 to show the gamer bull again, because that's the default one for bull, okay? So let's call perform upkeep. That's done. Let's now check the current price. That should update to 38 something. There we go, it has. And now we do token URI. And if we do that, we should expect this to change to gamer bull. And it has, right? Now, the good thing is because we're using this JSON format, right? When you put this onto Rinkeby, and that's going to be your homework, when you put it onto Rinkeby, you can see it update. It may take a couple of hours because sometimes, Rinkeby will be as quick as Rinkeby is, a few seconds here and there. But when you can then see it in OpenSea, right? If you connect your test Rinkeby wallet to OpenSea, you should be able to see your your NFTs minted, and they should change. They may take some time to show the change though, but you'll see that the name changes. Like you'll see if it's called Gamer Bull, or you'll see if it's called Beanie Bear. Even if the image hasn't actually updated, because that gets cached for quite a while on OpenSea, you'll see that the name changes, so you know it's still a dynamic NFT. Okay, so with that, we're done with the two most important parts of this particular smart contract for now, which is we know how to use keepers to automate contract executions. Chainlink Keepers can help you automate a bunch of your smart contract execution. In this case, Chainlink Keepers automates checking for price feed changes and accordingly updating our NFT to make them truly dynamic. The second thing we do here is that we use the price feeds to actually check whether or not the NFT needs to change. So two of the Chainlink services are being used here. Okay, so it looks like we've done quite a bit here, right? We've actually done quite a lot. And now for your assignment, what I'd like you to do is add random functions to this. Okay, so Chainlink randomness. I'd like you to add this to our NFT ERC721 smart contract with the tokens. And how do we want to use it? Well, we know that anytime the market goes up or down, accordingly, we will either be showing bull URIs or we're going to show bear URIs, right? We know that. But right now, we're only showing the 0th one, the first one in each of these arrays. What we want to do is choose a random one, right? So anytime the market moves and we're either choosing between bulls and bears, we have 3. And if you want, add as many JSONs as you like, as much metadata as you want, have as many as you want there, but make sure that you return one of these random ones, right? Random 0, 1, 2, 3 index, one of them, right? Or if you have 10 of them, 0 to 9, some random number there, right? Now, there's a little bit of thinking that you're gonna have to do about it, but the good thing is there's already a GitHub repo with the solution up there. Just look for the branch called randomness and look in that branch. But a couple of tips that I would give you so that you have the right direction is, first I would go to, I'd go to the docs, right? So docs.chain.link, go to the EVM chains. You'll see that we've already done, let's see, we've done data feeds. That's where we're getting our price feeds for BTC USD. We've done automating contracts. That's keepers. We've talked about connected API, but we haven't done it as part of the smart contract because I really just only thought these 3 would be good for you to start with. And we're going to use randomness. So that's the bit that is going to be part of your homework assignment. Just go to the get a random number bit and you'll see that it's actually really solid documentation, right? So let me quickly take you through some of the key concepts. One of the key concepts here is that you have a subscription manager. So let's click on that for a sec, right? Now, a subscription is basically you subscribe to the Chainlink oracles to send you a random number, right? But to do that, like I mentioned, you need to fund the distributed network of oracles to actually run the computation. And obviously, cryptographically guaranteed randomness on a blockchain is a very hard problem, right? You can read the documentations to know more. So you do have to fund a subscription. So I've created my subscription here. I'll be deleting this shortly, so don't try and use it. But you can create a subscription by going here, choosing this is your wallet address, so make sure your wallet's connected. If it's not, it'll prompt you. You create the subscription and you add some link tokens to it. And that subscription is, you pass the subscription ID, which in my case, for example, there are a whole bunch of recent subscription IDs here, right? 3397. You can pass that into your actual smart contract. And let's see how we do that. You end up extending our smart contract by using VRF consumer base version 2, because we're now in VRF version 2, which has some really substantial improvements. So you add this is VRF consumer base 2 to our ERC721 smart contract. That's where you start. And then note that there are a bunch of state variables, which you don't need to have, but there's no harm having them as you test and debug, and you add a bunch of values into the constructor. You can do all this in our existing smart contract. So you update the existing smart contract to do that. And you'll see that things like the subscription ID and stuff need to be passed. So if you look at the repo in the randomness branch, you'll see that I've done all this. I've even added some setter functions to help us change things around. But most of our change in logic will end up being in the update the URIs, right? The update all URIs. It'll be in the perform upkeep, calling update all token URIs. You'll have to think through, when do you want to ask for a random number? When you get the random number, where does the URI updating logic sit? Think through all that, right? It's a good engineering challenge for you, but and a lot of the solutions already there on the repo, but try not to cheat. Anyway, so let's see how we actually, what the intuition around using randomness is, right? So again, because we're saying it is a VRF consumer base 2, you end up having to implement two functions, right? There are two functions called request random words and fulfill random words. Words, think of it as numbers. They are numbers, right? The data type is a number. Now, so you call a coordinator contract, and you can pass the coordinate. So the coordinate is already given in this for the actual documentation. You'll see that the coordinator is already here. This is the Rinkeby coordinator, right? You can find, if you're using other networks, you can use some of the other contract addresses, but since we're using Rinkeby, stick to Rinkeby. All of this, I built it based on Rinkeby. You'll see the coordinator address is already there. That's just a smart contract that you call in your code in order to get the random number, right? So when we extend the ERC 721 contract, the bull and bear contract that we're working on, we call, you can call a request random words one if you want, and then basically call coordinator.request random words, pass in all the details at once. Numwords is the number of random numbers you want. I think on Rinkeby, check up the documentation, but I think you can get up to 500, right? We only need one because, well, that gives you a bit of a clue about how to implement it, but we need one. You can get two. In this example, there's two, but numwords is two, but we really need one for us. Callback gas limit, because we're doing some expensive computations. In the example, it's 100,000. I would say bump it up to 500 or 600. That's fine. And you can look at the documentation to see what the maximum is on that as well. And so request confirmations, you can stick to 3. That's fine. Subscription ID and key hash. Subscription ID we just talked about. And the key hash is this value here that tells, again, is given in the docs, which tells us, the max price that gas can be bumped to. So you pass all that to request randomness. And then there's a callback, right? Which is what this callback gas limit applies to. When I said set it to 500, that's the amount of gas that we're saying the callback is allowed to have to execute its function. Now, the fulfilling random words is where we receive an array of the random words that we requested in request random words. So we request it and we get the values in a separate function via a callback. So we need to implement both a request random words and a fulfill random words. We need to implement both of these functions in our contract since we are extending VRF consumer base v2, right? So you need to figure out how to apply this logic so that once you receive the random word, in our case, the random number, you can then figure out, based on whether it's a bear or a bull market or bull trend, whether or not you're showing, which of the array of IPFS URLs you want to show. Right now, we're all defaulting to the first one, index 0. But depending on how many you have in your array, right now we have 3. So you need to calculate a random number between 0 and 2, right? And use that as an index to get a completely random thing. And that's it. That's pretty much all you got to do. So you will need to update, refactor some of this to either add it in this logic or, add it in the perform upkeep. I think you'll need to add some logic in perform upkeep that calls another function that calls fulfill, calls request random words, and then receives the callback. And then the actual updating, the setting of the token URIs will need to be done once we receive it in fulfill random words, once we receive the random values in the callback, right? So you'll have no problems figuring it out. The documentation is awesome at Chainlink's VRF documentation is really, really good. You'll have no trouble. And I've already done it for you in the GitHub repo, so you can check the randomness branch to see the answer. So I hope you guys found that really useful. We've run through a lot. There's a lot to take on, I know. But once you get the hang of it, it's really life-changing kind of stuff, especially for blockchains, because you can now start to interact with data off-chain. You can get secure, verifiable, cryptographically truthful information about the real world into your blockchain, thus solving the Oracle problem. You can do randomness, which is impossible really to do in a deterministic blockchain environment. So it has to be done using really advanced off-chain sort of cryptography and deliver it in a decentralized way using Chainlink oracles. And you learned about keepers, which is an incredible way to automate the execution of your smart contract code so that things just keep humming along. Okay. It's been a blast, and I really hope you've enjoyed it as much as I have and learned a lot too. I think you now have a really solid sense of the power of Chainlink Oracle networks and the kind of functionality, power, and use cases that you can unlock with your big ideas just by using a hybrid smart contract. Today, we used 3 really cool Chainlink services. We use data feeds, we use the automation of Chainlink Keepers network, and we use Chainlink VRF randomness to get cryptographically provable randomness. Guys, you've done a lot. So treat yourself to a cookie and keep hacking. And if you want to dive deeper, get involved in the community we have. Hack more, learn more, check out these resources behind me, especially our starter kits, which can get you up and running with smart contracts and really cool tooling like Hard Hat and Truffle really quickly. Okay, so thanks again and go be awesome. See you soon.